Hey, welcome back. We've been talking about all of the major ideas in a typical physics course, everything you essentially need to know for a high school physics class. And some of these lessons I've done are starting to connect from multiple locations, and this is one of those times. So this is going to be a quick lesson. This is really crucial, though, to understand conservation of energy concepts along with simple harmonic motion. So we've talked about conservation of energy in terms of a swing problem where I've done the math and shown you how to work out a conservation of energy swing problem. I'll put a link in the upper right for that. And now we've also talked about simple harmonic motion just recently as well. And that's where you're going to have the restoring force for something like a pendulum. This pendulum is in simple harmonic motion as well. That restoring force is going to be proportional to the displacement from the equilibrium position. And if what I just said does not make sense, I'm going to put a link in the upper right so you can listen to my lesson on that as well. So hopefully it will make sense with time. Alright, and so what I want you to look at is this animation because again, this is a pendulum system and this is going to be undergoing simple harmonic motion. And if we're working with a system where there is no loss of energy to the environment whatsoever, it's an isolated system, there's no loss of energy due to air resistance or really just mostly friction, could be sound and heat as well, but mostly we're talking about loss of energy due to friction. And in a system like a pendulum swinging through the air, that would be air resistance. So if you had something like this, it could swing essentially forever. The total mechanical energy would not change because there's no loss of energy from the system. It would be just converting from one form into another. So if we take a look at this, the potential energy, I forgot to put a 0 down below here and write like a maximum up here, but the potential energy when it's at its left highest point right about now, that potential energy is going to be at a maximum, right? And then it swings down to the equilibrium position right now. You see where the equilibrium position is? That's where its kinetic energy is at a maximum. And then its kinetic energy goes down to a minimum again. So it hits a minimum at the very beginning where it's at its highest point. Essentially, it comes to a stop, right? And its minimum over here at the ending point, it comes to a stop as well. So that's why I should have a 0 down here, suggesting that its kinetic energy at those points are going to be 0. But that's where its potential energy is the highest. And so this is a cyclical process if there's no loss of energy. If I were to plot this graph over time, you would have just multiple cycles like this just going on forever unless there was a loss of energy to the environment. If there was a loss of energy to the environment, what would this green line here look like? What do you think? What would the total mechanical energy line look like? Well, it would be a negatively sloping line, right? Over time, you would be losing energy, and that would what's called dampen and come to a stop. And that's what we see in the real world. Things like this eventually dampen. If you have a system like a grandfather clock or a very massive clock, it would have a very heavy what's called a bob down below here, and air resistance would be largely negligible. In any case, that's just a really important visualization, I think, of some really crucial ideas we've been talking about for conservation of energy, and now that we've talked about simple harmonic motion as well, that can make sense as well. Alright, and I'm going to be covering all of the major topics in a typical physics course for the entire year. I hope you've enjoyed this. If you have any comments, let me know down below, and have a great day.